The topic we'll be discussing in this lecture is memory protection. So basically here we'll be discussing how memory can be protected with paging technique. When we are using paging, how memory can be protected. Okay. So memory is protected basically by adding some additional bit to the page table. So this additional bits, whatever we are adding, this will ensure protection in certain context. Okay. So say for example, if a particular memory is a read only, if a particular location is is a read only location, then that can be represented by a particular by adding an extra bit to the page table, which says that whatever that location, it is a read only location. Okay, that is the user is not supposed to write to that location. Okay, so we know that the page table contains the respective frame number of the particular page. Okay, so the page table basically index, the index is nothing but the page number. So page 0 may refer to page 5, page 1 may refer to page page 0 may refer to frame 5, page 1 may refer to frame 15, page 2 may refer to frame 9, all these things. Here we add one more bit. Okay, this bit will say whether the resultant memory location out of this whatever you are getting, that will be a read-only location or not. So this bit will say whether it is a read-only location or not. So if it is, maybe if it is 1, it is a read-only. If it is 0, then it is not read-only. It is a, you can perform write operation also. So this extra bit will say whether the particular memory location which will come out of this. So this is just a frame number. From this frame number and the offset will get the physical address. So that particular physical address, what is that? It's a only or not. So that can be represented by adding an extra bit which says whether it is read only or not. Okay, so not only one bit, like that we can add more bits which indicates whether it is read only, whether write access is allowed, or whether execute only. So basically we have three types of access privilege: read, write, and execute. Okay, so if it is read only, then this bit will be set. If it is write, then this will be set. So write in the sense read is also allowed. If it is execute, then this will be set. Okay, if everything, so if you want to, in such cases you can add three bits. So we'll add three bits: read, write, and execute. Okay, if all three are allowed, then all the three bits will be 0, will be 1. If only execute is allowed, then only execution will be 1. Okay, like that. With extra bits, we can specify some level of control. Okay, so control is also protection, right? So if it is read only, then it is one form of control. If it is write, it is one form of control. If it is execute, it is some other level, right? Okay. Sometimes the page table may also have valid or invalid bit. Okay. Apart from this, the page table may also have valid or invalid bit, which says whether the particular process is allowed to access this particular location or not. If the particular user is allowed to access that location, then the valid bit will be 1. Otherwise, the valid bit will be 0. Or instead of 1 and 0, it may be represented as V or I. V represents valid and I represents invalid. Okay. So let us discuss this with an example. So consider this particular case where the sorry where the logical address space is where the logical address space is. So this is the logical address. The logical address space is 2 to the power 14. That is 14 bits are used to address the logical address. So maximum how many locations it can address, in the sense 2 to the power 14 locations it can address. What is 2 to the power 14? 2 to the power 14 is 2 to the power 14 is 16,383 locations. Okay, so basically the logical address space is 16,000. It contains 16,383 locations. Okay, right? So the logical address space is totally, it contains 16,383 locations. Okay, and and let us let us assume that a particular process, say a process P1, the particular process P1, it is allowed to access, it is allowed to use, okay, a particular process is allowed to address only from locations 0 to 10,468. Okay, okay, so that particular process, it can access only up to 0 to 10,468 locations. Okay, it is allowed to access only this many locations. It cannot access beyond this, right? And let us assume the page size is 2 kilobytes. Okay, page size is 2 kilobytes. Sorry, so the page size is 2 kilobytes. Okay, so this is the scenario. So the scenario is what? The logical address space is 2 to the power 14 locations. It is 14 bits are used to address the logical address. So totally it can address this many locations, 2 to the power 14 locations, 16,383 locations it can address. Okay, and but a process P1, but a particular process P1 is allowed to access only the locations 0 to 10,468. Okay, and the size of each page is 2 kilobytes. Okay, so totally there will be how many pages? Each page is 2 kilobytes. Total location is 16,383. So here, so this total location of this logical address space is, total locations of this logical address space is 16,383. Okay, 383. So this is the total address space, right? So how many totally how many pages will be there? As each page is 2 kilobytes and totally there are 16,383. So you just divide 16,383 by 2 KB, 2 kilobytes. Okay, 16,383 by 2 kilobytes. 2 kilobytes is nothing but what? 2 kilobytes will convert it to bytes. Okay, 2 kilobyte, you convert it to bytes, because generally each location we call it as 1 byte, right? So if you convert 2 kilobyte to byte, so 1 kilobyte is 1024 bytes. Okay, 2 kilobyte is 2048 bytes. Okay, so if you divide 16,382 383 by 2048, what will you get? Yes, so so if you divide 16,000, so you need to divide 16,000 by 2048. Okay, so if you divide 16,383 by 2048, so you are getting uh, so so you are getting around 7.99. So say 8. So it is 8 pages. So totally there are 8 pages. Totally using this particular 14-bit address, there will be totally 8 pages. Okay, there will be totally 8 pages. But this particular process P1 is allowed to access only up to the location 10,468. Okay, where is this 10,468 is coming? Let us try to understand. Let us try to understand this. So first page, if you see, it is it is 0 to 2047, that will be occupied by the first page. The second page will be 2048 to 4096, that is up to 2048 to 4095. Okay, right, because 2 kilobytes, each page is of size 2 kilobytes. Okay, and the third page will be You just add another 2048, that is 6144. That is, I mean, third page in the sense, second page. The zeroth page is up to 2047. First page is up to 4095. Third page is up to from 4096 to 6144. Okay, I mean second page. Then the third page will be up to uh, 8191. Okay, so the fourth page will start at 8192. So fourth page will go from 8192 to 8192 to 10,240. Okay, 10,000, actually 10,239. Okay, right? And the fifth page will start at 10,240 to 10,240 to this 12,287. Okay, 12,287. And the sixth page will start at 12,288. Okay, right? Because each page size is 2 kilobytes, so that it is like this. Now the question here is, now the point is, if you see, the process one, it can access up to 10,468. Where is this 10,468 comes? It is a part of page 5, because page 5 starts at 10,240. So it is somewhere in between 10,000, it is somewhere in between page 5. Okay, it is so this process p1, it can partially access page 5, it cannot access fully page 5. Page 5 it can access up to this location 10,468. It is not supposed to access anything beyond that. Okay, but if you see the page table page table 0 is mapping to frame 2. And and is it a valid? Yes, it is valid. Page table 1, page 1 is mapping to, sorry, page 0 is mapping to frame 2, it is valid. Page 1 is mapping to frame 3, it is valid. Page 2 is mapping to frame 4, it is valid. Page 3 is mapping to some frame, it is valid. Page 4 is mapping to some frame, it is valid. Page 5 is mapping to frame 9, it is valid. Okay, I'll come back here later. Page 6 is mapping to some frame, but that is invalid, because this process cannot go beyond page 5. That is very clear, because other pages are not in its limit. Okay, but this 10,468 is a part of page 5. Okay, so page 6 and 7, you can clearly see it is invalid. So it means that this process cannot access page 6 and 7, but it still can access page 5. It can access page 5, but in page 5, how we will set this limit? So in page 5, then it may access even 10,469th location, which it is not allowed to access. Because here the page table says the valid, it is valid. Accessing page 5 is valid. Okay. So this is a problem here. Okay. The problem is that this particular process is allowed to access a particular, up to a particular location, which is coming somewhere in between page 5. Okay, but beyond that location, it is not supposed to access. But in the page table, for that particular page, the valid bit is set. Okay, now how we can overcome this problem? So now, say for example, it is page 5 is what you call, page 5 is mapping to frame 9, frame 9. So if the offset is, so page 5 starts at 10,240. Okay, so if the offset is 300, what will happen? If the offset is 300, then 10,240 will be added with 300. What you will get? 10,540, which is not allowed to access. But actually here it is a valid bit, so it may allow to access. So how could we control that? How could we ensure that this particular process should not access beyond 10,468 in spite of having a valid bit here? So what should we do in the sense? So this can be achieved by using by using page table limit register. Already we have discussed there is something called as PTL, it stands for page table limit register. So to ensure that this particular process does not access beyond that particular 10,468 location, So the page table limit register should contain the maximum length this can access. Okay. So PTBR will hold the starting address of this particular, what do you call, so the length of this particular uh, page. Okay, so the length, so maximum how many locations it can access, in the sense it cannot access beyond 10,468. The starting address is 0, so up to 10,468 it can access. Okay, so now whenever an offset is created, now whenever an offset is what do you call it? Whenever the offset is created, the offset, after adding it uh, with the starting address of that particular page. Okay, so we discussed that starting address is 10,240. It should not go beyond 10,468. If it goes beyond 10,468, then it should not be allowed to access. Okay, so this is how it can be controlled. So basically, this problem can be rectified by using PTLR, page table length register. Okay, so any violation in that, if the process is trying to access a location which is beyond its limit, then the hardware will automatically create a trap to the kernel. So trap is a hardware interrupt. Okay? So this is how protection is achieved in paging. Fine, let us stop here. Thank you.